Hello friends, welcome to this lecture of inner product spaces. In this lecture we shall study orthogonal vectors and orthonormal vectors and some results relating to these type of vectors. I have written here definition. We shall see the meaning of these. First definition is of orthogonal vector. It is relative to another vector. If u and v are vectors in V, vector space V, then u is said to be orthogonal to V if the inner product of u and v is equal to 0. If the product is 0, then the two vectors are said to be orthogonal. Or this concept is in dot product. We know the dot product of two vectors orthogonal means the similar to perpendicular, or it is if the two vectors are perpendicular, if vector u and v are perpendicular, then their dot product is 0. So it is similar to that. Orthogonal means perpendicularity relation between two vectors in dot product, and thus the dot product of two perpendicular vectors is 0. Here we say the two vectors are orthogonal if their inner product is equal to 0. Dot product is an example of inner product. Next, if u is orthogonal to v, then v is also orthogonal to u. That is again true for perpendicularity relation. If u is perpendicular to v, v is also perpendicular to u. And here in this case, the inner product of v with u is conjugate of the first property of inner product, conjugate of inner product of u and v. And because u is orthogonal to v, it is 0. The inner product is 0, complement of conjugate of 0 is 0, and thus this is a relative if we or symmetric. If u is orthogonal to v, v is also orthogonal to u. The next definition is w is subspace of v. If w is subspace of v, the orthogonal complement of w denoted by this notation w perpendicular sign. Orthogonal complement of w, we read it as orthogonal complement of w is, and write like this, and is defined by orthogonal complement of w is equal to those elements, those vectors in V such that its inner product with w is equal to 0, and this is true for all w belongs to w. That means those vectors x belongs to V such that inner product of x with V, x with w is 0, then we say x belongs to the orthogonal complement of w. So that is the meaning of orthogonal complement. And now we shall prove a lemma that is orthogonal complement of w is subspace of V. So thus we have to remember these two definitions. The vectors are said to be orthogonal if this inner product of u and v is 0, and we have to remember this also. Orthogonal complement of w means those vectors in V, the inner product of that vector with any vector in w is equal to 0. That means all those vectors in V which are orthogonal to every vector in w, orthogonal to, this means inner product of x and w is 0 means x and w are orthogonal, and therefore those vectors which are orthogonal to every vector in w, that set is denoted by orthogonal complement of w. And we will now consider this result as orthogonal complement of w is subspace of V. For this purpose we shall prove this lemma now. Let we will take two vectors in this orthogonal complement of w, and let us suppose the vectors be AB. Let AB belongs to orthogonal complement of w, and we take alpha beta scalars, that means that belongs to F. Now to prove this is a subspace, we have studied subspace earlier. To prove it is a subspace, we have to prove that it's a linear combination. Take any two vectors in that set and take its a linear combination with these scalars. Then the linear combination will be alpha a plus beta b. That also belongs to this set, that means orthogonal complement of w, then that becomes subspace. We have to prove that to show this is subspace. subspace of V. We shall show that alpha A plus beta B combination, linear combination of these two vectors in this set is also belongs to the same set, means orthogonal complement of W. Now let W belongs to W be any vector. Now for any vector W belongs to W, we have. Now when this will be in the orthogonal this vector is in this orthogonal complement of W, if its product with any W, see this, when we say X belongs to orthogonal complement of W, inner product of X with W is 0. So therefore that we have to show that inner product of this vector with W is equal to 0. We have inner product of alpha A plus beta B with W is equal to, and if this is 0, then this vector belongs to the orthogonal complement, X belongs to this. So then the result will be proved. Now it is easy to prove. See, we shall use the linearity property, third property of inner product, and that will be alpha into inner product of A and W plus beta into inner product of B and W. And this is alpha. What is the inner product of A and W? That is 0, because A belongs to orthogonal complement of W. If A belongs to orthogonal complement of W, then inner product of A with any element of W is 0. So by definition, and therefore this is alpha into 0 plus beta, this is also 0, because B also belongs to the orthogonal complement of W, and this is 0 plus 0, which is 0, and this shows that the inner product of this combination of A and B with W is 0, means this alpha A plus beta B also belongs to the orthogonal complement of W. So this shows that alpha A plus beta B belongs to, and this proves, thus this becomes subspace. So therefore this is, hence the orthogonal complement of W is a subspace of V. So this proves the result. Now we write a remark here as we will see that W intersection with orthogonal complement of W is 0. So how it is so? For that purpose, let X belongs to, or W belongs to, you can say, W belongs to W intersection orthogonal complement of W, and that means W is in W, W is in also orthogonal complement of W, and therefore W is see, it is orthogonal, self orthogonal, because inner product of W and W will be 0, because W belongs to orthogonal complement of W. So this implies W belongs to both, and therefore it is orthogonal complement. Therefore W is self orthogonal. It is self orthogonal, that is inner product of W with W is equal to 0, and this we know by second property of inner product, this implies W is equal to 0, W must be 0. So this implies and implied by W is equal to 0, and thus if W is in the intersection of this, or we can write this as a double implication from this, and then that is a double implication of this, and therefore W is 0, and thus the intersection of W with its orthogonal complement is 0. Now we shall consider, or we shall prove, the next lemma as lemma number 4. So this we have to remember, the two vectors are orthogonal if their inner product is 0, and the vector x belongs to orthogonal complement of W if its inner product with W is 0 for all W belongs to W. Next lemma is lemma number 4. If Vi we shall consider is the, or before proving the next result, we shall now prove orthonormal vectors, and then we will consider this next lemma. Now we write the definition for orthonormal vectors. The set Vi of vectors in V is said to be orthonormal if there are two conditions. First, each Vi is of length 1. Vi, we may consider the vectors, any set of vectors V1, V2 up to Vn, and that set is said to be orthonormal if each Vi is of length 1. That is, what is the meaning of length 1 or norm 1? Length means norm of a vector, and we know the length is defined as norm in terms of norm. So actually this norm of Vi is 1, or the inner product of Vi with Vi is equal to 1. That is, inner product of Vi with Vi, same vector, is equal to 1. And second, the inner product of Vi and Vj, inner product of Vi with Vj is equal to 0 if I is not equal to j. That means if these suffixes are different, means the two vectors are different, then their inner product is 0. Or this means the different vectors are orthogonal to each other. Their inner product is 0 means these two will be orthogonal, and thus orthonormal will have two conditions. First, the vectors, different vectors in that set pairwise must be orthogonal, and further each vector must be of length 1. So this is similar concept to unit vectors, perpendicular unit vectors. See, in a dot product we have the perpendicular unit vectors along x, y, z axis we have denoted by I, j, k. So these are orthonormal. These vectors are also orthonormal because they satisfy the first condition. Length of each vector is 1. These are unit vectors and their lengths is each having length 1. So suppose this is I, j, k vectors along x, y, z axis. Then they are mutually perpendicular, so we have the length of each vector is 1, and further they are orthogonal to each other. That is, we have I dot j is equal to j dot k is equal to k dot I is equal to 0. They are perpendicular. That means pairwise their product dot product is 0. So this is an example of orthonormal vectors. Ijk unit vectors, mutually perpendicular unit vectors are orthonormal. So thus there are two conditions. First is each vector in the set must be of length 1, and second is they are pairwise orthogonal. That means Vi and Vj. If I is not equal to j, then it is 0, and if I is equal to j, then it is 1. So these are the two conditions. Now we shall state our next lemma. Lemma number 4. If Vi is set of set of orthonormal vectors in V, then Vi are linearly independent. Then the set Vi is linearly independent. Further, if we can consider W as, if W belongs to V, or W belongs to V, and W is having this expression alpha 1 V1 plus etc. alpha n Vn, then alpha I is equal to W into Vi for each I, for I taking value 1, 2, 3, etc. So this lemma now we shall prove. So Vi is, if it is orthonormal set, then it is linearly independent. Every orthonormal set is linearly independent. That is the first result. And how to show a set of vectors is linearly independent? We know by definition of linearly independent. Suppose these are V1, V2 up to Vn vectors. So we shall write the solution for this or proof of this. Let Vi, this set, we will write as V1 up to Vn, be orthonormal set. In V, vector space V. Now we shall consider the combination of these vectors. Let further, let alpha 1 V1 plus so on up to alpha 2 V2 etc. and in intermediate I shall write this as alpha I Vi plus so on up to alpha n Vn is equal to 0. And if you consider this combination is equal to 0, when this set will be said to be linearly independent if each alpha is equal to 0. We have to show, we shall show that each alpha I is equal to 0, I taking value 1 to n. Now we will take the inner product of this with Vi, all these vectors with Vi, that is this combination alpha 1 V1 plus so on up to alpha I Vi plus alpha n Vn. This is one vector. This is one vector combination of V1 to Vn, and we take its inner product with the vector Vi. Any vector we have considered Vi. So this is equal to, for now for any Vi belongs to this set V. And now we will use the linearity property, that is property third of inner product, and write this as alpha 1. This is equal to, I shall write here, this is equal to alpha 1 inner product of V1 with Vi plus so on up to alpha I inner product of Vi with Vi and plus so on alpha n inner product of Vn with Vn. So this is the bilinearity property we have. And now because Vi are orthonormal set, so Vi is orthonormal set, since is orthonormal, we have, see what we will have by definition of orthonormal. We have Vj Vi is 0 if I is not equal to or j is not equal to I. That is this condition. Vj Vi or Vi Vj is 0, and Vi inner product of Vi and Vi is equal to 1. So that is this first condition. And see, using this in this expression, then from 1. So this is equal to, so from 1, then see or see, we should consider this as, this is the combination we have written as 0, and therefore in this inner product this is 0 comma or 0 inner product of 0 and vi. So this will be 0 and vi inner product, and that is equal to 0. So therefore we should write like this. So this implies the inner product of this combination with vi, because this combination we have assumed as 0, so it is 0, and now therefore this will imply the left side is this much and the right side is 0. So this is equal to 0, and this we shall suppose as 1. This we shall suppose as 1. Now we shall use this condition in this one. So what will be the left side expression using this? See, if these suffixes are different, then the product is, inner product is 0, and if the suffixes are equal, then the inner product is 1. So here v1 and vi, this is v1 vi, so therefore these are different, it is 0, and so on. Here vi, inner product of vi with vi, and these are equal, so therefore this is 1, and again others will be different, only this will exist and remaining will be 0. So by this condition, therefore from 1 we have, then 1 becomes, now what 1 will be, the left side will only be alpha I into 1 is equal to 0, that is alpha I is equal to 0, or that means, that is alpha is 0 for each I. I taking value 1 to n, and this is what we have to show. Each alpha is equal to 0. This shows that the set vi is linearly independent. This is the condition for linearly independent vectors. Hence, or thus, the set vi is linearly independent. And thus if the set is orthonormal, then it is linearly independent. That is the relation that we have to remember. If these are orthonormal, then they becomes linearly independent. Now the next result is let w belongs to v and w having this expression, that is obvious second part in this lemma. Let w is equal to, next if w is alpha 1 v1 etc., then the inner product of this w with vi we shall consider. Inner product of w with vi is equal to, so what is this is the same as earlier, alpha 1 v1 plus so on up to alpha n vn and inner product with vi. We have expressed this inner product here in the earlier part, and that is alpha 1 inner product of v1 vi plus so on up to alpha n inner product of vn and vi. Now this product will be alpha I into 1 as earlier. So because these vectors are again orthonormal, and therefore this is equal to alpha I as earlier. And thus we have alpha I is equal to the inner product of w with vi for each I taking value 1 to n, and this proves the lemma. So this proves the lemma number 4. Now we shall state one more lemma, that is lemma 5. If vi is a set of orthonormal vectors in V, again, then W belongs to V, we shall consider. then the vector u, we will form the vector u like this: w minus inner product of w with v1 multiplied by v1 minus etc. inner product of w with v2 into v2 minus so on, and the general term we will write as minus inner product of w with vi into vi, and minus the last will be inner product of w with vn multiplied by vn. Is this vector is w is orthogonal to each v1, is orthogonal to each v1 v2 up to vn. So this is the result that we shall prove. Now the proof. So this is also depending on orthonormal set, and we have to use the definition of orthonormal set of vectors to prove these results. First we shall consider it is given vi are orthonormal. That means vi satisfies these two conditions. Now what we have to prove, this u is orthogonal to each of v1 v2 vn, means u is orthogonal to vi. So that we shall have. Now for any vi, I taking value 1 to n, we have inner product of u and vi. Now to show these are orthogonal, what we have to show? We have to show u is orthogonal to this one, any one vector, that means vi, and u will be orthogonal to vi if their inner product is 0. That we have to show, and it is easy to show. So this will be equal to inner product of v with inner product of u with vi. What is the expression of u? That is here. So I shall write below, this is equal to inner the expression for u is w minus inner product of w with v1 multiplied by v1 minus, I shall write the intermediate term, that is minus inner product of w, this term we have not written, it is to be assumed this is w inner product of w into v2 etc. So this is the ith term in this expression, and minus, it is continued, minus inner product of w with vn, and then we have to write vi. So the space is less, so I shall write like this. So this is, in short, I shall write inner product of w with vi into vi, inner product of w with vn, this is minus vn with vn, this much is u, this much is u, and its inner product with vi. This is what we have, this is minus dot dot minus. So you should see we have written the expression of u as first component u here, and inner product of this u with vi. We use linearity property, and this is equal to inner product of w and vi minus, this is a scalar, it is inner product, we know the result is in field, and therefore this is a scalar, this is a constant, actually it has a value in the field, and we have to take the inner product of v1 with vi. So this will be inner product of w and v1 into inner product of v1 and vi. So that is the linearity property here, and minus, now here w, inner product of w with vi into inner product of vi with vi, this ith term we have written, intermediate term we have written, minus, that is continued, and what is the last term? This will be constant, inner product of w and vn, and then inner product of vn and vi. So inner product of vn vi. So this is the expression, and now we use the fact that these are orthonormal. the vectors Vi are orthonormal. That means Vi satisfies these two conditions. Now Vi are orthonormal. Vi is orthonormal set. Therefore, what we have is Vj Vi is 0 if j is not equal to I, and Vi, inner product of Vi with Vi is equal to 1, second and first. Now thus what will be the expression of this? Therefore we shall suppose this as 1. Therefore from 1, what is the left side? Left side is inner product of u with Vi, any vector between v1 to vn, and this is now see this inner product of w into Vi will remain the same, w and Vi. Now what about this vector? We use here Vj, inner product of Vj and Vi is 0 if j is not equal to I, and here this will be 0 because 1 and I are different. So this is 0, next will be 0, only this will be 1. Inner product of Vi with Vi is 1, remaining will be going to be 0. Suppose Vi is V5, then it will be inner product of V1 and V5, that is 0. Next term will be inner product of V1, again see this will be inner product of V2 with V5, and that will be 0. If the suffixes become equal, that is the important property of orthogonality, if the suffixes become equal then it is 1, otherwise it is 0. So here in this expression starting from the second term, here this is independent of Vi, inner product of Vi with Vj, so this will remain, and for this the remaining expression only this term will exist because other terms will have different suffixes and they will be, the inner product will be 0. So therefore this we have the first term, and next is minus, this will exist, that is w, inner product of w with Vi into 1, and remaining will be 0, and that means only this will exist, or otherwise we can write this as 0 etc. So minus 0 etc. minus, and this will exist, inner product of w with Vi into 1, and minus 0 etc. remaining will be all 0, only this will exist, and thus again you see this is inner product of w and Vi minus inner product of w and Vi, and therefore it will be equal to 0, and thus so therefore we have started with this, left side is this one, and this is equal to 0. Difference of these two is 0 using the orthonormality property. And if this is 0, what this suggests? These two are orthogonal, hence u is orthogonal. So this happens for all I, hence u is orthogonal to Vi for each I, and that means u is orthogonal to V1, V2, Vn, and this completes the proof. So thus we have studied in this lecture orthogonal vectors and orthonormal vectors and properties relating to orthogonal and orthonormal vectors. So orthonormal, both these are important, and we have to remember and understand these orthogonality and orthonormal vectors. So thank you for watching the lecture.